our next speaker is Lee Rosenthal of Caltech, talking about the California Legacy Survey population statistics with an expanded catalog of RV detected exoplanets. So take it away, Lee.
Thanks, Josh. Can you see my screen all right?
Yes, I can see.
Okay.
Though I see speaker notes.
That is the wrong screen. Is that better?
I'm still seeing speaker notes. There you go.
Okay.
Just updated now. Got your title slide.
Great. All right. Thanks. Okay. Hi, everyone. Thanks to the LLC and the SOC for the opportunity to present, and many thanks to my advisor, Andrew Howard, and my collaborators in the California Planet Search team for their support. I'm here to talk about a 3-decade radial velocity survey of bright nearby stars, which we are using to explore exoplanet occurrence across several axes. Our motivation for this study is to learn more about planet formation and dynamics by studying exoplanet demographics with a uniformly constructed catalog. Also, as astronomers develop extremely precise radial velocity instruments, as we discussed in Lauren Weiss's breakout session, this work may assist future searches for Earth analogs by revealing whether stars that host cold gas giants, which are detectable today, are more likely to host small habitable zone planets, which will be detectable with EPRV instruments someday. Previous RV survey success stories include the Keck Planet Search, published in Coming et al. 2008. This Keck high-res survey found that 10% of all FGKM stars host a gas giant within 5 AU. Up until this paper, this broad occurrence rate was completely unconstrained. This survey also measured how planet occurrence varies with orbital period, shown here with a cumulative distribution on top and a binned occurrence on the bottom. For reference, 1,000 days corresponds to about a 2 AU orbit for a sun-like star, and the water ice line for sun-like stars is 2.5 AU. So this occurrence bump near the ice line was a key result showing that giant planets are abundant where the protoplanetary disk is richer in solid material. This survey used...
If I can interrupt for a second, we're still seeing your title slide.
Geez. Has it updated?
There we go.
Okay, thanks. So this survey used 8 years of RVs through 2004, and we have collected more RVs for all of these stars since then. There's more work to be done to measure occurrence out to 20 years or more, corresponding to 8 AU, well beyond the ice line. On the opposite end of the mass and period range, the ADA Earth survey used high cadence Keck high-res data to measure the occurrence of close-in small planets and disprove the idea that there should be a planet desert between 5 and 30 Earth masses. Kepler validated this result shortly thereafter. So the California Legacy Survey is a continuation of these and other CPS surveys covering 719 bright stars. Our data mostly comes from the Keck high-res spectrograph. This instrument has been taking radial velocities since 1996, which means that many of our stars have 24-year baselines. We supplemented with data from the Automated Planet Finder and Lick Hamilton spectrographs at Lick Observatory. We performed careful stellar selection for this survey without prior knowledge of hosted planets so that our survey statistics are trustworthy. We don't want to only look at planet hosting stars and find that 100% of all stars host a gas giant, for example. We will publish all RVs and associated stellar activity and Doppler fitting metrics when the first paper in this series is accepted. We are currently responding to the referee report. So what do we do with this data? We look for planets. BJ Fulton, Leah Hirsch, and I wrote an algorithm, RV Search, to discover planets in radial velocity data sets. RV Search can also measure its search completeness on a given data set, which is essential for occurrence measurements. We will make this code available as a Python package alongside our first paper. We applied RV Search to the California Legacy Survey and detected 165 known planets, as well as 15 new discoveries that made it through our vetting process. Here's our planet catalog against the backdrop of median search completeness for our survey, where color increments by 10% for each different shade. And our discoveries push down below 10 Earth masses and out to 10 to 20 AU. We can combine our catalog and completeness contours to make a wide range of occurrence measurements. For instance, while the first paper in this series will report the details of our stellar and planet catalog, the second we'll return to the occurrence work of Coming et al. 2008, this time pushing far beyond the water ice line. BJ Fulton will be leading this work. So this plot shows our preliminary results using a piecewise constant model. The dashed blue line is just a simple histogram of planets. The solid line shows the posterior peak for our occurrence results that take search completeness into account. And the vertical lines and gray histograms show the variance of the posterior. There are two key features on this plot. One is a sharp jump in occurrence around 1 AU, and another is a tentative occurrence fall off from 3 to 10 AU. We need to do more work to validate this result, but if real, this might say something about the inward migration of gas giants or about a lack of in situ giant formation beyond 8 AU due to low gas or planetesimal density. After that paper, we will use our catalog to measure the occurrence of outer gas giants given the presence of inner super-Earths. Even our sparsest and shortest baseline data sets are sensitive to a Jupiter mass planet at 3 AU. And just to showcase our sample, here are all of the planets belonging to systems that host both a detected small inner planet and a detected outer giant. So the trickier measurement is the occurrence of inner small planets given the presence of outer giants, since most of our data sets are not sensitive to planets below 20 Earth masses. However, most of the data sets belonging to stars that do host gas giants are sensitive to close-in planets above roughly 15 Earth masses. We will try to place a lower limit on this conditional occurrence rate using this sample. So one preliminary finding without numbers is that small planets rarely cohabitate with warm giants. Note the empty space on this plot above 100 Earth masses and within 2 AU. This might mean that close-in gas giants suppress small planet formation. Follow-up work should elucidate this. I'm also interested in learning about planet formation pathways by studying eccentricity distributions. Recent studies have jointly fit the eccentricities of many planets to compare and contrast distinct groups, such as singles and multis or planets and brown dwarfs. I've started similar work with our sample, which includes over 110 giants and a handful of substellar companions. This plot shows a comparison of single giant systems and multi-giant systems with peak eccentricity histograms and draws from a population fit. So we see a long tail for single giants that doesn't exist for the multis. This is due at least in part to a simple fact: paired planets can just only be so eccentric before they cross orbits and scatter each other. However, these distributions may also say something meaningful about the excitation mechanisms for giant planets. Maybe planet-planet scattering is the main source of these lonely, highly eccentric gas giants, and weaker interactions give rise to the moderate eccentricities of paired giants. Future work will use our sample to test this idea. So I'll leave you with a gallery of the longest period planets from our survey, made possible by multi-decade monitoring with high-res. And so, of course, thanks to everyone at Keck who runs the telescope and makes this work possible. And if you have ideas for how to use this data set, please reach out to me via this talk Slack channel. Thanks for listening.
All right, thank you, Lee. I had a question on your previous slide. This might be a bit naive, but I noticed in the eccentricity plot, at small eccentricities, the behavior of the multis and the singles diverged. One, went very large and one went very small. Why is that?
Yeah, that's a great question. Part of that is just an artifact of the model we're choosing. This is a beta distribution. So a lot of work has been done with this. For example, Kipping et al. 2013 fit this sort of simple 2-parameter flexible distribution to all of RV discovered planets to sort of find a population eccentricity distribution. So that sharp downturn for the multis, I think, is just an artifact of the model. So future work would use some more sophisticated, maybe something non-parametric to measure these distributions. But it does seem like there is a peak in circular orbits for the singles. That seems real.
Great, thank you. Other questions? I'm not seeing anything come in just yet. I don't know if my feed is delayed. I'm also curious, how will the arrival of KPF influence this data set? Is it just going to be a nice continuation and you'll get N more years tacked onto all of these?
Yeah, that's a great question. I think we're still discussing ideas, but the main thing that I'm interested in is using our current data set to try to learn whether stars that host giant planets are more likely to host small maybe habitable zone planets, and then use KPF to target. If that's the case, then use KPF to target the stars that we think are more likely to host small planets. But that's definitely a work in progress.
All right, thank you very much.